Welcome back, deep divers. Ready to explore something, well, pretty much everywhere.
I'm always ready for a challenge, so let's go.
Perfect, because today it's all about nitrogen. You know, atomic number 7, the N on that periodic table. And I have to admit, it's something I've taken for granted, like it's just air, right?
You'd be surprised how much is packed into that just air idea. Nitrogen really is a fascinating element.
Well, then let's unpack it. What's got you so excited about nitrogen?
Well, for starters, it's not just here on Earth. When you zoom out and look at the Milky Way, our galaxy, nitrogen ranks as the 7th most abundant element.
7th. Wow, so it's a major player in the universe.
Absolutely. And it's the same story in our own solar system, so it's really woven into the fabric of, well, existence as we know it.
And speaking of being woven in, it's the main ingredient in our atmosphere here on Earth, right?
Right. About 78% of what we breathe is nitrogen in that diatomic form, N2.
N2. Okay, so 2 nitrogen atoms stuck together.
Exactly. And it's a colorless, odorless gas, the most common chemical species in the air we breathe.
It makes you wonder, though, why something so common seems so unreactive. I mean, we think of air as being pretty inert.
That's actually a crucial part of nitrogen's story. It was first isolated back in 1772 by Daniel Rutherford.
Oh, so this isn't some recent discovery.
No, it's been known for centuries. And get this, it was initially called azote, meaning no life.
No life. Sounds a bit ominous.
It was because it doesn't support combustion or respiration. Later, the name nitrogen stuck, highlighting its presence in niter or saltpeter.
Okay, so our mission for this deep dive is to get to know this element that's both everywhere and seemingly does nothing. We'll uncover its properties, the compounds it forms, and the, I'm guessing, surprisingly wide range of applications it has.
That's the plan. It's more exciting than you might think.
All right, then, let's start with the basics. The nitrogen atom itself. What makes it tick?
So a nitrogen atom has 7 electrons. 2 hang out in the inner shell, and then 5 are in the outer, or valence shell.
Valence shell. Those are the electrons that do all the bonding, right?
Yeah. You got it. Now, in that valence shell, 2 electrons are in the 2s orbital, and 3 are unpaired in the 2p orbitals.
And this arrangement is important
Because it dictates how nitrogen interacts with other atoms, how it forms bonds.
And one key consequence is its electronegativity, right?
Bingo. And nitrogen pulls hard on electrons. It has an electronegativity of 3.04 on the Pauling scale.
3.04, that's pretty high, isn't it?
It is. Only chlorine, oxygen, and fluorine are more electronegative. So nitrogen really wants to hog those electrons when it forms bonds.
Makes sense. What about size? Is a nitrogen atom big or small?
It's on the smaller side. Its covalent radius is about 71 picometers.
Picometers. Those are tiny.
They are. It's smaller than boron and carbon, but bigger than oxygen and fluorine, its neighbors on the periodic table. But things change if it becomes an ion.
Ah, ions. Those charged atoms.
Right. If nitrogen gains 3 electrons to become the nitride ion, and Fe, its radius nearly doubles to about 146 picometers.
Whoa, that's a big jump. So gaining electrons really puffs it up.
You could say that. Now, another important thing about nitrogen is its ionization energies.
Which are?
It's basically the energy needed to rip an electron away from an atom, and nitrogens are very high, especially the first 3. It takes a lot of energy to form positive nitrogen ions, so you don't see them very often.
Nitrogen prefers to share electrons, not give them away.
Got it.
Now, this next bit is interesting, but I need a little help understanding it. What's the deal with the lack of radial nodes in the 2p subshell?
Okay, so imagine electron orbitals as 3D shapes around the nucleus, where electrons are most likely to be found.
I kind of picture them as blurry clouds.
That's a good analogy. And these radial nodes are like gaps in those clouds, points where the probability of finding an electron drops to 0.
Okay, I'm with you so far.
Now, nitrogen, being a small atom in the first row of the p block elements, doesn't have these radial nodes in its 2p orbitals.
And this matters because
it impacts how nitrogen's orbitals overlap when forming bonds. It's one reason for its high electronegativity and also why it doesn't form more than 4 bonds easily, unlike some larger elements.
So no radial nodes, strong pull on electrons, limited bonding capacity. It's starting to make sense.
Exactly. And these quirks are why nitrogen's chemistry is so distinct from heavier elements in the same group, like phosphorus.
Right, they're in the same column of the periodic table, but
They have the same number of valence electrons, which governs their bonding tendencies. But those subtle differences in their atomic structure, like the radial nodes, really make a difference in how they behave.
it's like they have the same blueprint, but different construction materials.
That's a great way to put it. Now, speaking of bonding, nitrogen isn't as good as carbon at forming chains with its own atoms.
Right. Carbon chains are everywhere in organic chemistry.
Exactly. But while long chains of nitrogen atoms aren't common, nitrogen does form nitrides with carbon.
Nitrides. So nitrogen bonded directly to carbon?
Yes. And these carbon nitrides can form all sorts of interesting structures. Chains, sheets like graphite, even cage-like structures like fullerenes.
So nitrogen might not be a chain maker on its own, but it's quite versatile when partnered with carbon.
Absolutely. It's actually an active area of research in material science. Now, here's a fun fact. Nitrogen shares some similarities with oxygen.
Really? They seem pretty different.
Well, they're both highly electronegative, meaning they attract electrons strongly.
Right, we talked about that.
And they both participate in hydrogen bonding, although oxygen's is stronger.
So they can form those weak interactions between molecules.
Yep. And they both can act as electron donors in coordination complexes, using their lone pairs of electrons.
Lone pairs. Those are pairs of electrons not involved in bonding.
Right. You can even see analogies between ammonia, NH3, and water, H2O, in how they can gain or lose protons.
So despite being in different groups on the periodic table, they have some common ground.
Exactly. Now, where nitrogen really excels is in forming multiple bonds.
Multiple bonds.
Yeah.
Like double or triple bonds.
Exactly. And it loves to do this with carbon, oxygen, and other nitrogen atoms.
This is where those poop interactions come in, right?
You got it.
Yeah.
This is how the incredibly stable N2 molecule with its triple bond is formed. That bond is super strong and hard to break.
Which explains why nitrogen gas is pretty unreactive.
Exactly. It also explains its low melting and boiling points. The N2 molecules don't interact much with each other.
Because they're so content being triple bonded together.
You could say that this is a stark contrast to its heavier relatives like phosphorus, which prefer single bonds and form bigger molecules.
So nitrogen likes to keep it simple and strong.
Pretty much. Oh, and one more thing about nitrogen bonding. It forms a wide range of compounds with phosphorus.
So even though they're different, they can still play together.
Exactly. You get chains, rings, even cage-like molecules. It's a whole world of chemistry to explore.
Sounds like it. Okay, let's switch gears and talk about isotopes. Nitrogen has two stable ones,
Okay.
NON and NN. What's the difference and why should we care?
So almost all nitrogen on Earth is a mixture of these two. About 99.6% is ion, the lighter one.
And the rest is ion.
Right. The key difference is the number of neutrons. Both have 7 protons, which defines them as nitrogen.
Protons determine the element, neutrons.
They add to the mass. Ion has 7 neutrons, Orionon has 8. So ion is slightly heavier.
And this small difference matters because...
It affects how they behave in chemical and physical processes.
You mean like how fast they react or move around?
Exactly. It's called isotopic fractionation. For instance, when plants absorb nitrogen or bacteria process it in the soil, they might prefer one isotope over the other.
Interesting. So the ratio of ion-EM can vary.
It can. And even something like ammonia evaporating can cause fractionation.
So by measuring these tiny variations, scientists can track nitrogen's journey through different systems.
Absolutely. Like tracing its path through ecosystems or geological formations. It's like a fingerprint.
Ion has some special uses, right?
It does. It was discovered in 1929, and it's great for a technique called nuclear magnetic resonance, or NMR, spectroscopy.
NMR. It's like a molecular MRI, right?
Exactly. And AM gives much clearer signals than NN, making it easier to study the structure and behavior of molecules.
Yeah. But there's a catch, isn't there?
There is. Orion is less abundant and less sensitive than NMR, so scientists often use samples enriched with Aron to get good data.
But once they have those enriched samples, the nitrogen atoms stay put, right? No swapping with the atmosphere.
That makes long-term studies much easier, and the ratio of Aron to Aron, often expressed as delta N, or Aron, is super useful in many fields.
Like geochemistry, you said.
Yes. And hydrology, paleoclimatology, paleoceanography, all sorts of things. It helps us reconstruct past environmental conditions and understand present-day processes.
It's amazing how much information we can get from just a tiny difference in mass.
It is. And it's not just the stable isotopes. Nitrogen also has radioactive ones.
Radioactive, so they decay over time.
Exactly. Most have very short half-lives, meaning they vanish quickly. But one, Orion, has a half-life of about 10 minutes.
And that makes it useful for
medical imaging, specifically positron emission tomography or PE scans. But because it decays so fast, it has to be produced on-site using a cyclotron.
So no stockpiling radioactive nitrogen.
Oh, then there's Orin, which is important in nuclear reactors.
But it decays in seconds.
Just over 7 seconds, yes. But during that time, it emits high-energy gamma radiation.
Sounds dangerous.
It can be, which is why nuclear reactors have strict safety measures. But that radiation also helps detect leaks in the cooling system.
It's incredible how nitrogen, in all its forms, can be used in such diverse ways.
It really is. Okay, let's move on to allotropes.
Allotropes.
Yeah.
Different physical forms of the same element, right?
Yeah.
Like diamond and graphite for carbon.
Exactly. Now, with nitrogen, you have atomic nitrogen, also called active nitrogen, which is highly reactive.
Atomic nitrogen. So just individual nitrogen atoms.
Yep. Each with 3 unpaired electrons, making it a triradical. It really wants to form bonds.
Sounds like something you'd want to keep a safe distance from.
You can make it by passing an electric discharge through nitrogen gas. It gives off a peach-yellow glow.
A glow.
Yes, and that glow can linger for a while even after the discharge stops. It's called an afterglow.
So even as it's recombining to form N2, it's still giving off light.
Pretty cool, huh? But the nitrogen we know and breathe is molecular N2, or dinitrogen.
That's the colorless, odorless gas we talked about earlier.
Right. It's also diamagnetic, meaning it's not attracted to magnets. And its defining feature is that super strong triple bond between the 2 nitrogen atoms.
Like triple bond is really the key to its stability, isn't it?
Absolutely. It takes a lot of energy to break it. That's why N2 is so unreactive at room temperature.
But it's not completely inert, right? There are some things it can react with.
True. Very reactive metals like lithium can react with it directly. And it can also bind to certain transition metal compounds, which is important for catalysts.
Catalysts. Those are substances that speed up chemical reactions.
Right. And speaking of reactivity, there's research on nitrogen oligomers and polymers.
So longer chains of nitrogen atoms.
Exactly. These could be very energy-rich, potentially useful for new explosives or propellants.
Sounds like a high-risk, high-reward area of research.
Definitely. And under extreme conditions, like immense pressure and high temperature, scientists have created a polymeric form of nitrogen called nitrogen diamond.
Nitrogen diamond, because it's structured like diamond.
Yep. With strong single bonds throughout. It's super dense and stable under those conditions.
So from a simple gas to a diamond-like solid. Incredible. And back at normal pressure, nitrogen becomes a liquid at very low temperatures.
77 Kelvin, to be precise. And it looks like water, but it's much less dense.
And that's liquid nitrogen, used for all sorts of cooling applications.
Exactly. And it freezes solid at even lower temperatures, forming different crystal structures.
It's amazing how diverse nitrogen can be in its physical forms. And speaking of diversity, its chemistry is even richer.
It is. There's a whole world of nitrogen compounds out there.
Let's start with the nitrogen complexes. These seem to be key to understanding how that seemingly inert nitrogen molecule can be activated.
They are. These complexes were a major breakthrough. The first one discovered was a ruthenium complex where N2 binds end-on to a ruthenium ion.
End-on meaning one nitrogen atom attaches to the metal.
Right. This discovery provided a model for how nitrogen might interact with metals in biological nitrogen fixation.
That's the process where bacteria convert atmospheric nitrogen into ammonia, right?
Exactly. And it also provided insights into how industrial catalysts work in the Haber process, which produces ammonia on a massive scale.
So understanding these complexes is crucial for both natural and industrial processes.
Absolutely. And since then, we've found 5 ways the nitrogen can bind to metals.
5! Wow. So end-on, side-on.
Yes.
Yeah.
Side-on, where the metal interacts with the triple bond, and bridging modes, where N2 connects 2 or even 3 metal atoms.
It's like nitrogen is playing a molecular game of Twister.
Haha, kind of. Now, the bonding in these complexes is similar to how carbon monoxide binds to metals.
Carbon monoxide, that's CO, right?
Yep. But dinitrogen is generally a weaker electron donor and acceptor than CO.
Meaning the metal-nitrogen bond isn't as strong?
Generally, yes. And studies show that the initial donation of electrons from nitrogen to the metal is more important for bond formation than the back donation from the metal to nitrogen.
So nitrogen is more of a giver than a taker in these relationships.
You could put it that way. And end-on binding is usually more common than side-on.
So dinitrogen complexes are pretty common now.
They are. We've made hundreds with almost every transition metal on the periodic table.
That's a lot of chemistry.
It is. And they come in various colors depending on the metal and the surrounding ligands. White, yellow, orange, red, brown, all sorts of hues.
Now let's talk about nitrides, azides, and nitrido complexes. I was amazed to learn that nitrogen can bond with almost every element except the noble gases and some really unstable ones.
It's pretty remarkable. These binary compounds with nitrogen bonded to another element are called nitrides, and they have a wide range of properties.
Some are ionic, like salts, others covalent, like diamond, and some even have metallic properties.
Exactly. And many elements can form multiple nitrides with different metal-to-nitrogen ratios. It's a diverse family.
And how do you make these nitrides?
You can react a metal directly with nitrogen gas or ammonia, often at high temperatures.
Sounds intense.
It can be. Another way is to decompose metal imides, which contain metal-nitrogen bonds with hydrogen attached.
So you're essentially stripping away the hydrogen and leaving behind the metal-nitrogen bond.
Precisely. Now, those salt-like or ionic nitrides are typically formed with alkali and alkaline earth metals.
Like lithium nitride and magnesium nitride.
Yes, they're like salts of the nitride ion N, although the bonding isn't always purely ionic.
And then there are the azides with the azide ion N.
Right. Alkali metal azides like sodium azide are well known, but alkalides of B subgroup metals are less ionic, have more complex structures, and are often very explosive.
Explosives. So, handle with care.
Absolutely. Then you have the covalent binary nitrides like cyanogen, phosphorus pentanitride, and silicon nitride.
And silicon nitride is a very hard, high-melting material, right?
Yes, it's a very useful ceramic. The group 13 nitrides like boron nitride and gallium nitride are also interesting.
I read that boron nitride can exist in forms similar to graphite and diamond.
It can. That's because it's isoelectronic with those forms of carbon. So you get materials with very different properties from the same elements, just arranged differently.
That's fascinating. And gallium nitride is important for electronics and LEDs, right?
Absolutely. It's a key semiconductor material. And the nature of bonding in these group 13 nitrides changes as you go down the group.
So boron nitride is more covalent and indium nitride is more ionic.
That's the trend. Now, there's also this analogy between boron-nitrogen chemistry and carbon chemistry.
I read about a compound called borazine, dubbed inorganic benzene.
Right. It has a ring structure with alternating boron and nitrogen atoms, like benzene's carbon and hydrogen ring.
But the analogy isn't perfect, right?
Not quite. Boron is electron deficient, making borazine more reactive than benzene.
So they look alike, but behave differently.
Exactly. Now, finally, there are the interstitial nitrides, where nitrogen atoms fit into the gaps in a metal's crystal structure.
These sound like they would be very strong materials.
They are, like titanium nitride and chromium nitride. They're very hard, opaque, and chemically inert with high melting points.
And they conduct electricity.
Yes. They often have a metallic luster, too. They hydrolyze very slowly, so they're quite resistant to water.
So they're tough cookies. And what about the nitritoanion as a ligand?
Ah, yes. The nitritoligand, known, is triply bonded to a metal center and is the strongest pi donor ligand we know.
Pi donor meaning it donates electrons in a specific way.
Right. These nitrogen complexes are usually made by decomposing azide complexes or deprotonating ammonia molecules bound to a metal.
So you're manipulating the ligands around a metal center to create the nitrito complex.
Exactly. Now, the lineoazide anion can form lots of coordination complexes, but longer chains of nitrogen atoms are rare.
But not impossible, right?
Right. A tetranitrogen species with a -4 charge, NO, has been observed.
Wow, so 4 nitrogen atoms linked together. Okay, let's move on to nitrogen's hydrides. Ammonia is obviously the superstar here, essential for fertilizers and countless other chemicals.
It is. It's made on a massive scale worldwide. And that pungent smell.
Unmistakable. But why is it so important?
Well, it can form hydrogen bonds, which gives it some interesting properties.
Hydrogen bonds, those weak attractions between molecules.
Right. They give ammonia a surprisingly high melting and boiling point for such a small molecule. It's also a good liquid solvent.
So those hydrogen bonds are really influencing its behavior.
Absolutely. They're weaker than the ones in water, though, because nitrogen is slightly less electronegative than oxygen.
So oxygen hogs those electrons a bit more in water.
Exactly. Now, ammonia acts as a weak base in water, accepting a proton to form the ammonium ion, NHO.
And it can also act as a very weak acid, losing a proton to become the amide anion, NHO.
It can. And it even undergoes a tiny bit of self-ionization, like water.
So it reacts with itself to a small extent.
Exactly. Now, while it doesn't burn easily in air, it will burn in fluorine, producing nitrogen trifluoride.
Nitrogen trifluoride, that's NF3, right?
Yep. Its reactions with other nonmetals can be quite complex, and it reacts with heated metals to form nitrides.
So lots of reactivity going on there. What about the other hydrides, hydrazine and hydrogen azide?
Hydrazine, N2H4, is a fuming liquid with a smell similar to ammonia.
It's also used as rocket fuel, right?
It is. It burns very rapidly with oxygen, releasing a lot of energy, and its physical properties are surprisingly similar to water.
Really? Similar melting and boiling points.
Yep. Now, it's a kinetically stable compound, meaning it doesn't decompose easily, even though it's thermodynamically less stable.
So it's happy to exist as it is, even though it could release energy by breaking down.
That's a good way to put it. It's also a good reducing agent in chemistry, and it's a weaker base than ammonia.
Right, how is it made?
By reacting ammonia with sodium hypochlorite in an alkaline solution, usually with gelatin or glue present.
Gelatin. What does that do?
It helps to prevent unwanted Sive reactions. Now, hydrogen azide, HN3, is something to be very careful with.
I read that it's very explosive.
Extremely. Even dilute solutions are dangerous. And it's toxic, too. It has a pungent, irritating smell and can be lethal.
Not something you want to mess with.
Definitely not. It's the conjugate acid of the azide anion, and its acidity is comparable to the hydrohalic acids.
And how is it made?
Usually by reacting aqueous hydrazine with nitrous acid, under very controlled conditions, of course.
Makes sense. Okay, moving on to halides and oxohalides. We know all 4 nitrogen trihalides exist, but many are unstable. Nitrogen trifluoride seems to be the exception.
It is. NF3 is a Ni3, or more commonly its adduct with ammonia, is extremely shock sensitive. It's a classic demonstration in chemistry classes.
The one where it explodes with a little touch.
That's the one. And then you have chlorine azide and bromine azide, which are also incredibly sensitive explosives.
Definitely compounds to handle with extreme caution. What about those nitrosyl halides and nitryl halides?
These are 2 series of reactive gases. The nitrosyl halides are NOF, NOCl, and NOBr.
And the nitryl halides?
They're FNO2 and ClNO2. Both series are potent halogenating agents.
So they're good at adding halogens like fluorine or chlorine to other molecules.
Exactly. They have specific uses in chemical synthesis.
Okay, now for the oxides of nitrogen. Nitrous oxide, N2O, or laughing gas, is probably the most familiar.
It is. It's used as a propellant in whipped cream and was formerly used as an anesthetic.
Hence the laughing gas nickname.
Right. It's produced by heating ammonium nitrate carefully. Structurally, it's NO, and it's fairly unreactive at room temperature.
But it does decompose at higher temperatures.
Yes, above 600 degrees Celsius, it breaks down by breaking the nitrogen-oxygen bond.
Now, nitric oxide, NO, is interesting because it has an odd number of electrons and plays a role in our bodies.
It does. It's a signaling molecule in mammals. It's also a byproduct of ammonia oxidation.
That high-temperature process used to make nitric acid.
Exactly. Now, NO is a colorless gas and has unpaired electrons, making it paramagnetic. It's not very stable at high temperatures, though.
So it likes to react with things.
It does. It reacts with oxygen to form nitrogen dioxide, with halogens to form nitrosyl halides, and it can bind to transition metals to form nitrosyl complexes.
Lots of reactivity going on there. And it can exist as a dimer, right?
Yes, at very low temperatures, 2 NO molecules can pair up to form N2O2.
So even simple molecules can have complex behavior.
Absolutely. Now, dinitrogen trioxide, N2O3, is a blue solid that readily decomposes into other nitrogen oxides.
It doesn't like to stay as N2O3 for very long.
Nope. Then you have nitrogen dioxide, NO2, and its dimer, the nitrogen tetroxide, N2O4, which exist in equilibrium.
Equilibrium meaning they're constantly converting between each other?
Right. NO2 is a brown gas, while N2O4 is colorless. Both are formed by decomposing metal nitrates, and they react with water to make nitric acid.
And N2O4 is used as a rocket fuel oxidizer.
It is. It reacts spontaneously with hydrazine-based fuels, making it very useful for rocket propulsion.
That's pretty intense. And lastly, dinitrogen pentoxide, N2O5, is the anhydride of nitric acid.
It is. It reacts with water to form nitric acid. It's made by dehydrating nitric acid, usually with phosphorus pentoxide.
But it's not the easiest compound to work with, is it?
It's not. It's very reactive, light-sensitive, and potentially explosive. It's a powerful oxidizing agent.
So, handle with care.
Definitely. And its decomposition can involve the formation of the nitrate radical, NO3, which is very reactive as well.
Lots of interesting chemistry going on there.
Absolutely. Okay, let's shift gears to oxoacids, oxoanions, and their salts. Hyponitrous acid, H2N2O2, is a weak acid that plays a role in the nitrogen cycle.
It's involved in the biological conversion of ammonia to nitrate.
Exactly. It's an intermediate in that process. Its acidic solutions are stable, but it decomposes in basic conditions.
Breaking down into nitrous oxide and hydroxide ions.
Right. Now, its salts, the hyponitrites, are more stable, especially towards reducing agents.
And they can act as reducing agents themselves.
They can, and the hyponitrite ion can also act as a ligand binding to metal ions.
So it's a versatile little ion.
It is. Now, nitrous acid, HNO2, is another important player, though we haven't isolated it in its pure form.
But it exists in solution, right?
It does, and it's a common region in chemistry. It's made by acidifying nitrite solutions.
And it's used in organic chemistry for making diazonium salts.
Exactly, which are very useful for creating a wide variety of aromatic compounds.
And sodium nitrite, one of its salts, is used in food preservation.
Yes, in small amounts. It helps cure meat and prevent bacterial growth, but it can be toxic at higher concentrations.
So everything in moderation.
Exactly. Now, the nitrite ion, NOO, is also a common ligand in coordination chemistry.
Meaning it can bind to metal ions.
Right. And it can bind in two ways. Through the nitrogen atom, called nitro, or through an oxygen atom, called nitrito.
So it has options.
It does. This can lead to interesting isomerism, where you have two different structures with the same formula.
Okay, now for the big one. Nitric acid, HNO3.
The king of nitrogen oxoacids. It's one of the most widely used acids in the world.
Discovered by alchemists centuries ago and now produced on a massive scale.
Absolutely. It's made by oxidizing ammonia and is crucial for fertilizers and explosives.
And the anhydrous form, pure nitric acid without water, is a bit tricky to work with.
It is. It's a solid at room temperature and decomposes when it melts. The liquid form also undergoes a lot of self-ionization.
Self-ionization, meaning it reacts with itself.
Exactly. It forms ions within the liquid. Now, nitric acid is a strong acid, and concentrated solutions are powerful oxidizing agents.
They can dissolve many metals.
They can, but some, like gold and platinum, are resistant.
What about aqua regia, that mixture of nitric and hydrochloric acids?
Aqua regia is even stronger. It can dissolve gold and platinum because it forms chlorine and nitrosyl chloride, which react with the metals.
So it's a potent combination.
It is. Now, in concentrated sulfuric acid, nitric acid can be protonated to form the nitronium ion, NUU.
Protonated, meaning it gains a proton.
Exactly. And this nitronium ion is a strong electrophile, important for adding nitro groups to aromatic compounds.
So it has important uses in organic synthesis.
It does. Now, the stability of nitrate salts varies a lot depending on the metal.
Some are stable, others.
Others decompose when heated. They can form nitrites, oxides, or even the pure metal, along with nitrogen oxides and oxygen.
So it really